Yeah, when a process you want to execute, I said it requires certain set of pages. Okay. Now consider those required pages are not in the main memory. Okay, but it resides in the secondary memory. So any process to complete its execution, it has to be given with required pages. Okay. So since at the given point of time the memory is already full, okay, so there is no space left out to brought pages from the secondary memory to main memory. Okay, so in that scenario we have to look into page replacement algorithms. What does it mean? All the pages which already resides in the main memory with respect to other process has to be replaced so that you can bring the required pages for the particular process from the secondary memory to main memory. Okay, so this in that scenario we need page replacement algorithms. Now the question is, you can't simply take out any pages which is present in the main memory to place other pages to the main memory from the secondary memory. So to do this task, certain algorithms are used. So in your syllabus, they have given first in, first out, least recently used algorithm, and optimal replacement algorithm. Okay, out of these three, in your lab, you need to implement first in first out and least recently used algorithm. Okay, so let's start with first one. So before that, let me read out the question given in the syllabus. Okay, yeah, so it is given that design, develop and implement a C or C++ or Java program to implement page replacement algorithms, that is least recently used. LRU stands for least recently used, and FIFO, that is first in first out algorithm. Okay, use assume suitable input required to demonstrate the result. So you have to implement these two page replacement algorithm either using C or C++ or Java. So I'm following Java programming since you're all you all have studied Java program in the last semester, right? So that's why I have considered Java coding. Okay. So before looking into the coding part, let's see the algorithm used for it. Okay. So first thing is what? It is the most simplest page replacement algorithm. In this algorithm, what happens? The operating system keeps track of all pages in the memory in a queue. Okay. So the oldest page which is in the front of the queue. Okay. Oh, anytime since queue follows first in first out, right? So the oldest page will be placed always, it will be at the front of the queue. Okay, and all the pages that is required for the process to execute which are placed in the memory are placed in a queue. Okay, so when a page needs to be replaced, so whatever the page that is present in the memory has to be replaced. The page which you are supposed to replace is the front of the queue. Okay, so the page which is present at the front, that means which is the oldest one, will be selected for the removal, the selected for the replacement. Okay, so the algorithm that I'll be following to implement this technique is, the first one is the capacity. I'll use a what array no variable, that is capacity. Okay, which holds, which says the number of pages that memory can hold. See, at a given point of time, say consider memory can hold 1,000 pages. Okay, but for this explanation purpose, I'll be taking it as 3 or 4. Okay, so at a given point of time, with respect to this example, I'll be considering the the capacity of the memory, okay, as 3 frames. Okay, so it can hold 3 pages at a time. Okay, next I'll be using set, okay, which which says the current set of pages in the memory. So set will depict how many pages are there uh, in the set. Okay, so that I'll be representing with the help of hash set, which is a package available in the Java program. Okay, then what I'll be doing, I'll start traversing the pages. uh, I said when a process need to be executed, it requires set of pages, right? So I'll start looking each and every page that is required for the process. I'll be looking for those pages whether it is present in the memory or not. Okay, so I'll be traversing the pages. Okay, the first thing is what? I'll check if the set. I said I have to check for the current status, right? So for that I'm using set. I'll look into the set if whatever the page that is required for the process, either it present in the set or not. Okay, so before doing that, I'll be comparing the set holds less pages than the capacity. Okay, I'm just comparing the number of pages that set holds with the capacity that I have considered in the beginning. Okay, then the particular page, whatever required for the process, that particular page. Okay, insert page into the set one by one until the size of the set reaches capacity. Okay, or that means if a particular process is not present in the set, that means if it is not present in the memory, then I'll keep on inserting those pages into the set. Okay, till where you can insert the pages into the set, till it what reaches the size of the capacity. Okay, that is one thing. And then what I'll be doing, simultaneously maintain the pages in the queue to perform FIFO. So once you insert in the set, the same will be, I'll be placing it in a queue because I have to replace first in, first out. No, the oldest page I'm supposed to delete. That should be replaced. Okay, not delete. That should be replaced. That's why I'll keep on yeah, what inserting those pages in the queue, okay, to perform FIFO operation. Next, if that is the case, then there will be a page fault. That means if the required page but for the process is not in the memory, then we call that as a page fault. At that point of time, we need to replace the pages in the main memory. Okay, so that is page fault. And then the next step, if this is false, I mean if this condition does not holds good, then the current page is in the set, then do nothing. If the required page for a particular process is already there in the memory, that means if it is already there in the set, then I need not to replace anything. That's why do nothing here. Okay, and the else part for this, remove the first page. That means if the set is full, if your memory is full, then what you have to do, obviously there will be a page fault, then you have to replace a particular page which is there in the main memory, right? So remove first page from where? From the queue, as it was the first to be entered in the memory. Okay, so when the memory is full, then you have to replace the pages. So in that case, I'll be selecting the one which is entered first in the memory. Okay, then replace the first page in the queue with the current page in the string. Okay, so what does it mean? The one which is entered first into the queue will be replaced with the page which you wanted to brought in from the secondary memory to main memory for the execution of particular process. Okay, that is one thing. And then I'm storing that current page in the queue. Okay, and since it is replaced, obviously we call that as there is a page fault, and I'm incrementing the page fault count. Okay, and at once you check out all the what required pages for the process, then if there is a page fault, you will be replacing the required page from the secondary memory to main memory. Okay, once it is done, then the counted page fault need to be written. That is what the last step is. Okay, this is what is the algorithm that I'll be following to implement first in first out. Okay, so now we'll see the problem, how to solve it. Okay, now consider P1, I mean any process, okay? Any process requires to complete its execution, it requires this reference string, okay? Here, reference string is what? The pages that is required to complete the execution of this process, okay? In the same order. First, it need page 1, okay? Then page 3, then page 0. After that, page 3, page 5, page 6, page 3. Okay, so in this order, the process need pages to complete the execution of this process. Okay, initially what? This is, consider this is the memory capacity. Okay, initially the capacity of this memory is 3 frames, 1, 2, 3. Okay, and consider it is initially empty. Okay, so now the thing is, to execute this process, operating system will see what is the first page required for this process. The first page required for this process is page 1. Okay, so now this page 1, the operating system will look into the main memory here, main memory, okay, whether it is present in the main memory or not. So as you can see here, this one is not present in the main memory. Okay, so if it is not present in the main memory, then we call it as there is a page fault here. Okay, that, or you can call it as page miss. Okay, so that's why I'll be writing here as page fault, and I'll be placing this one here. Okay, okay, one here. Okay, next, since one is there, it will start with its execution. Okay, next, I'm audible, right? Yes.
Yes, ma'am.
Okay. Next, the operating system will look into the next page required to complete the process of complete the execution of this process. So next page is 3. Okay. Now it will look into the memory whether this page is present or not. Is it present here? No, right? So one here. Since 3 is not present, I'm just carrying the same thing here. Okay. 3 is not present here. So there will be page fault here. Okay, page fault. So, and this 3 will be placed in the main memory. Okay, fine. Next, which is the next page required? 0. Okay, is this page 0 present in the main memory? This is 1, this is 3. Is this 0 present in the main memory? No, it's not, right? So that's why there again there will be page miss, that you can call it as page fault. Okay, so 0 will be brought into the main memory. Fine. Okay, this is okay. Next, after this, next required page is 3. So now operating system will look into the main memory whether this 3 is present in the memory or not. Since it is there, so no page fault occurs here. Okay, so at this point, no page fault occurs. Okay, now next, it will come to the next required page, that is page 5. Now Listen carefully. 5, it will check the main memory whether this page 5 is present in the main memory. No, it is not present. So when it is not present, then you can call it as, there is a page fault, right? When it is not there in the memory, that means there is a page fault. So now when there is a page fault, you have to place this required page into the memory. But as you can see here, the memory is already full, right? It is already filled. So now the thing is, you have to find a particular page here so that you can replace the particular page with the required page. As since we are following first in first out, you have to replace the page which you have entered first. In this case, it is 1, right? So 1 has to be replaced with the required page 5 and rest all remain same. Okay, this is how FIFO works. Okay, so now next, once 5 is done, next you check which is the next required page, that is 6. Okay, is the 6 present in the memory? No, it is not present, right? That's why there is a page fault, or you can say page miss, right? Page fault. So 5, yeah, 6, right? Now 6, when you check here, it is not present. Okay, now you have to, since the memory is full here, you have to replace any one page in this memory, right? Now which page you are supposed to replace? The second recently filled is, sorry. So second oldest, or what you can say, this is entered first compared to 0 and 5, right? So that's why this has to be replaced with the required page. Okay, so this remains as it is. 0 also remains as it is. I am replacing 3 with 6. Okay, so 3 with 6. Fine. So now next thing is what? Next required page is 3. Okay. So this 3, again it will be checked in the memory. Is it present? No, it is not present. That's why there is a page fault, and this 5 recently entered, 6 also recently entered. So the next thing is 0 need to be replaced with the required page. So 0 will be replaced with 3. Okay, so this is how first in first out works for this process with the given reference string. We call this as a reference string. Okay, so now you calculate how many page faults for this process with this reference string following FIFO. That is 1, 2, 3, 4, 5, 6. So for this problem, page fault is 6. Okay, this is how you implement or solve the problem for FIFO. Okay, this is FIFO. Fine, I hope this is clear to everyone. So the thing is, to implement this, we will be using Q. Okay, so that you can follow this principle, FIFO, first in, first out. Fine. So now we'll see the code implementation part. Okay, so as I already explained the algorithm that I'm going to follow here, I'll be using hash set. Okay, this is set which is has unordered the set is unordered here. Okay, so we just need following this, because whether, to check whether the required pages are there in the memory or not. Okay, and then I'm using Q here. Q is using to, I'm using Q here because to implement the memory, okay, which has to follow first in first out, right? That's why. And queue will be implemented with the help of linked list. Okay, so let's start with the program. So in the program, main program, okay, the pages array I have considered, where I have considered the reference string as 70120304233032. Okay, so this is the reference string I have followed, or you can follow the one which I explained now, that is 1 comma 3 comma 0 comma 3 comma 5 comma 6 comma 3. Okay, and the capacity I've taken for the problem which I solved now is 3. Okay, so the pages required for the process is 1303563, and the capacity in the sense size of the memory is 3. That means at a given point of time you can place maximum 3 pages. Okay, then I'll be calling page fault function. Okay, when there is page fault, then there you have to what perform page replacement. Okay, so let's see the particular function here. Okay, yeah, page fault. Okay, in this you see, to represent the current pages. Okay, how many pages are, I mean, what are the pages that are present in the memory? To keep track, I'm using set, which is nothing but a hash set here. Okay, so it is an unordered set, and I'll be using this to check if a page is present in set or not. Okay, and that is what I'm creating a set here, and the set name here is yes. Okay, and it can take the capacity, I mean, the size of this set can be capacity that I have considered for this program. Okay, that is given here. Okay, next, I'm using queue or I'm creating a queue here, that is indexes. Okay, and I'm implementing this queue with the help of linked list. Okay, now next, initially I'll assign page fault to 0. Okay, and then I have to check each and every reference string for the process uh, for the execution, right? So to keep track that, I'm starting with I is equal to 0 to n. Okay, now according to the algorithm, what is the first thing I have said? Uh, one second. Okay. Okay. So first thing is what? Uh, I I'm checking if the set can hold more pages. Okay. Here set function I'm using here. I'm sorry, size function I'm using here on set. Okay. So this function, size function returns the number of elements in the hash set. Okay. First, what I'm doing, uh, what are the size of the set, what is the size of the set for the created hash set. Okay, so the hash set name here is yes. Okay, on which I'm calling this size function. This size function will return the number of elements that is present in the set. Okay, initially it is 0. Okay, I'm not inserted any pages there, so that's why initially the size of S will be 0. Okay, and the size of this set can go till the capacity, that is 3. Okay, so that's why initially I'll be checking if the size is it lesser than capacity. Okay, if it is lesser, then what you can do, insert the particular page into the set. If not present already, if it is not present already, which represent page fault. Okay, so first we'll see first case, that is lesser than capacity. Okay, so as I said, initially it will be 0. Okay, for which one? For the first reference string, that is what is the reference string I considered? 1 here. Okay, so initially that thing. Okay, then that particular page, is it present in the I mean, is it contained in the set? It is not contained, it is not present, right? One is not present here, right? Yes, this is true. Then add that particular page to the set. Okay, I'm adding this particular page to the set. Okay, so since I'm adding it, obviously what does it mean? There is a page fault, so I am incrementing it. Okay, next, the same page I'm adding it to indexes. What it is a queue that I have created and I am implementing it with the linked list, right? So for on the queue also I'm adding it. Okay, so that is what the initial thing. Okay, so is similarly it will be checked for all the reference string. Okay, next, if the set is full, I mean once the set is full, the size of the set is 3, then need to perform FIFO. Once the size is full, then obviously you have to perform a replacement, right? So that is remove the first page of the queue from the set and as well as queue and insert the current page. Okay, so let's see that comes in the else part. That means if this condition fails, then else, where you will be checking the current page whether it is present in the S. It is not present, that's why you are performing a page replacement, right? So in that case, what you are doing, you are doing you are calling peak function. So peak function on indexes. So indexes is a queue, right? So here what does this peak function does? This pace, sorry, I'm very sorry, this peak function is used to view the head of the queue without removing it. That means it will return what value or the element is present at the head of the queue. That means the first inserted element into the queue. Okay, and that will be stored in a variable called val. Okay, so why I'm doing this? Because I have to remove the first page inserted into the queue when I am supposed to perform a page replacement. So that's why I'm taking the first inserted element to val. Okay, and then I'm calling poll function here. Okay, this poll function, what does it do? It removes the indexes page, the particular page. Okay, so I mean that one, and then sorry, this poll function removes the element which is present at the head of the queue. Okay, and then once it is removed from the queue, then I'm calling remove function and passing the value as val. That is the val, whatever considered here. That remove function, I'm calling it on the set to remove this particular value from the set. Okay, once it is removed, I'm adding the current required page to the set. That is s dot add pages of I. Okay, so next is what, once you include the page into the set, obviously again you have to include that page into the queue. That means you have to perform push operation. That's why indexes dot add of pages of I. Okay, when you include a push a new page into the queue, then obviously that means that is a there's a page fault, right? And I'm incrementing the page fault count. Okay, and this goes on till you complete all the reference string. Once it completes, you are going to return the page faults. Okay, that is how it works. For this reference string, the calculated page fault is 6. I hope this is clear to everyone. So now we'll take a problem and we'll trace it out. Okay, so just a minute.
Ma'am, you're not audible, ma'am.
I'm sorry, I muted. Okay, I'm sorry. Okay, so let's consider, where is it? Huh. Let's consider the implementation, how this problem is implemented with the along with the code that I explained now. Okay, initially this is the reference string I'm supposed to consider, right? And here, let me show you the code. Yeah. For what is the first thing I'm doing? I'm checking the size of the set with capacity. Okay. So as I said, initially none of the pages added to this set. So size initially it will be 0. Okay. So but it can take the size till the capacity value. Okay. So now, yeah. So for the first one, so it s is equal to, it can take the size 3 here. That as I said, the capacity, and have assigned page fault is equal to 0. Okay, let's start the iteration. Let's consider the first element in the array, that is pages array. Okay, I is equal to 0. That means the first element here, 1, right? So that I'm checking here. That is, if s dot size 0, is this 0 less than 3? Is it 0 less than 3? Yes, it is, right? If it is lesser, then what you have to do? You are checking that page is not present in the set, right? So yes, that particular page is not present in the set. You can see here, it is not present in the set. So in that case, you are going to add that particular page into the set. Okay, so you can see here, I'm adding that page into the set here. Okay, since you are placing that particular page into the memory, then obviously there is a page fault. So I am incrementing the value, that is, it has to be pf. Okay, pg, and I have written pg, make it as pf is equal to 1 now. Okay, once you add what once you add page into the set, next thing is what? You have to push the same page into the queue, right? So that is what I'm doing here. So in that case, what you have to write, as I said, I'm implementing queue with the help of linked list. So a linked list is represented like this, right? So one is pushed into the queue. Okay. So next, what is the next thing? Next, I'm going to increment I value. I is equal to 1. That means second string in the reference string 3. Okay. So again, I'm checking size of the set with the capacity s dot z, s dot size. That means here now s value, size of s is 1 now, right? I'm talking about size, not the page that is present in the set. Okay, the size. Okay, now this size lesser than 3, yes it is. That means 3 is not in the set, so I'm adding that particular 3 to the set. So since I'm adding it, there is a page fault, so it is incremented by 1. Now page fault is 2. Okay, once you add the page into the set, push it to queue. Okay, so that means I'm adding 3 to the queue now. Okay, I'm pushing 3 to the queue. Okay, and next, increment I value. Continue with the iteration. When I is equal to 2, that means the third page, that is page 0. Page 0 you have to consider. That means now size of the set is 2. Two elements are there. Size of the set is 2 now. 2 is lesser than 3? Yes, it is, right? So this page is not present. You can see here, the page 0 is not present in the set, isn't it? So I'm adding this page to the set here. Okay, I'm adding that here. So since I'm adding it, that means there is a page fault, so I'm incrementing it. Page fault is equal to 3 now. The same page I'm pushing into queue. That's why the 0 is added here. That means pushed into the queue. Okay, now increment I value becomes 3. That means next page in the reference string, that is this one, I is equal to 3 means this 3. Okay, page 3. Yeah, is this now you have to check the size with the capacity. What is the size of the size of the set here? 1 2 3. So size of the set is 3, right? So this 3, is it lesser than 3? No, it is not. So where the code will come, it will come to the else part. It will come to the else part. Okay. What you are doing in the else part? In else part, you are checking it. The particular page is not present in the set, right? So if it is not present, then you have to find which is the page that is present in the head of the queue. Okay, that you are going to place in val, and you are calling poll function which removes that particular page. Okay, so let's see that. So here, since 3 is lesser than 3, 3, this 3, it already present in the set, right? So if it is present in the set, what it means? Do nothing. Okay, so next, increment I value. I is equal to 4. I is equal to 4 in the sense next page in the reference string, that is 5. 5. Okay, check the size of the set is 3 here. Size of the set is 3. Is this 3 lesser than 3? Yes, it is. Check whether this 5 is present in the S. It is not present. So you assign this head of the queue. Which is head of the queue? Which is the first value that you have inserted into the queue? That is this one. This is head of the queue. First element pushed into the queue. So 1, that will be assigned to val. Okay, the speak function will return the first element inserted into the queue into the variable val. Okay, and then this poll function will remove this first element. Okay, that's why 1 is removed from the set. Now set contains 3 comma 0. You can see here 3 comma 0. This 1 is eliminated. Okay, 3 comma 0. Okay, since after eliminating, what you have to do, you can check in the code here. After removal, you are going to add this particular page into the set. Okay, so I'm adding this, which page? This 5. 5, I'm adding it to set now. So it is unordered set. Okay, you need not to worry where I have placed this 5. Okay, it is unordered set. You can place it anywhere. Okay, so now once you include the page into S, then what is the next step? You have to push the same page into the queue, isn't it? So indexes here 3. After 0, you have to insert 5. You can see here previous 130. You're going to discard this, right? You're going to remove this part. You're going to remove this part. So left out is 3 and 0, for which you are inserting the next element, that is 5. Okay, since you are replacing a page, that means page fault. You are incrementing the page fault here. Okay, next, increment I value. I value is 5. That means the next string in next page in the string is 6. Okay, so 6 here, and check the size. Size of the set is 3. 3 is lesser than 3. Yes. Is this 6 present in S? It is not present. So find the find the element that is present at the head of the queue, that is 3, that is placed into the variable val, and this particular 3 is removed from the set, right? And then the set will contain 5 and 0. You can see here I have removed 3, right? Since I removed 3, the left out elements are 5 comma 0, that is written here. Okay, and then uh, once uh, once you removed it, you have to add the new page to the set. That's why 6 is added into the set. Okay, and again the same page need to be pushed into the queue as well. So 6 is added here, inserted here. Okay, so since you added a new page here, I mean you performed a page replacement, obviously there is a page fault, so you are incrementing it to 5. Okay, again next increment I value, I is equal to 6. The last page required, that is 3. Is this 3 present in the, yeah, is this 3 present in the set? You have to check. Before that you are checking size of the set with the capacity, it is lesser. 3 is not present in the set. You can see here 3 is not present in the set. That means you have to remove the what element that is present at the head of the queue, that is 0, and this is removed from the set. Now set contains only 5 and 6, and the new page need to be inserted to this set. Okay, once it is inserted, the same page you need to push into the queue. Okay, so that's why 3 inserted here, and then increment the page fault. Now page fault is here, it is 5. You once you increment it, it is 6. Okay, in total you know that page fault, at the last you are going to return the page fault. So for this reference string, for the capacity 3, the output is, I mean page fault is 6.